Welcome back to week 9 of the Thermodynamics course, and in this week we'll continue to discuss on the second law of thermodynamics, and I welcome all of you back again for today's problem solving session. And once again, just to reiterate and keeping things in place, I am once again sorry for the abrupt change in the schedule of these problem solving sessions. That unfortunately, because I was not in station, I had to attend an international conference in the past 2 weeks. I was not able to attend, I was not able to conduct these sessions on time, and because of which I am having to postpone these sessions and post the recordings accordingly, so to aid all of you and the students, so that other students who can take the aid of these recordings to solve problems that are relevant to their assignments and exams. Okay, so once again I am sorry for the inconvenience caused. By this week all the postponed sessions or the pending sessions will be completed, and we'll resume with our regular schedule. Okay, so with that, let us discuss today's agenda. Again, it is similar to all the previous week's sessions, that I will briefly first go through the topics that were discussed by Professor Anand in the lectures, and of course I won't dive deep into each and every line or concept. Like, I will not thoroughly discuss each and every topic, but of course if there's any doubt, you may ask or put them in a discussion forum so that I can look into those doubts and clarify them. Okay, so moreover, after the end of these 12 weeks sessions, there will be an extra session before your exam. Basically it will be a doubt clearing session, so that if you have any doubt regarding all these problems that have been discussed in these 12 problem solving sessions, you can join that session and just discuss with me regarding the problems that have been discussed here. Okay, so it will be held on or before 16th of October, before your final exam of this course. So just to keep that in mind, I gave you a reminder. Okay, so yeah, there will be an extra session as well for this course, for this, at least for this problem solving part. Okay, so with that brief introduction, let us proceed. Okay. So in the last week we were discussing about the reversible and irreversible cycles, the thermal efficiencies, and we briefly discussed about the reversibilities and the irreversibilities. And now in the last week we were just briefly introducing about the the role of irreversibilities in a system, or how the presence of irreversibilities affect the efficiencies. We are discussing about that, right? We also discussed about the efficiencies of these heat engines, and we discussed about the coefficient of performance of your heat pumps and refrigerators. We discussed about that as well, and we discussed about the basic definition or the statement of the second law of thermodynamics. So for the perspective of this course, that is the basic classical thermodynamics, there were two statements that were given, that is the Kelvin-Planck statement and the Clausius statement, and both are one way or another quite elegantly describe the essence of the second law of thermodynamics. So as I mentioned in the last week, in through definition or in words, those two statements may seem different, but in its essence or its very core, these two statements are quite related with each other, and just are different ways to understand or explain the second law of thermodynamics. Okay, so when you study a bit more, or you become a bit more expert in this subject, you will see that you may be able to, like, you may have learned some more definitions, some different definitions for this second law, okay, and which are also correct in their own way. But for this basic introductory course for the classical thermodynamics, these two statements are these two are the standard statements. Okay, so now we start with the Carnot cycle and the Carnot theorems. So Carnot cycle is one of the cornerstones of classical thermodynamics, I would say, because this is a cycle. Just give me 1 second. This is an idealized cycle, or I must say imaginary cycle, which is used as a standard to what to say used as a standard to understand the working principles of different real life cycles. Okay, so you will eventually see that the efficiency of the Carnot cycle is the highest compared to any other cycle working between these two temperature limits. Okay, so even though this cycle does not exist in real life, but still uh, it, in its idealized form, it helps us to understand these concepts of thermodynamics, specifically the second law of thermodynamics, in a very simple and elegant way. That's why it's very important to understand this Carnot cycle. And you will see that in this session itself, that after understanding the Carnot cycle, you will be able to understand the Carnot theorems, and you will be able to how to say absorb this concept in a much better way after understanding the Carnot cycle. That's why it's important. So students usually ask that, say it's an imaginary cycle, it does not exist, it does not make any sense, then why are we studying it? So it's primarily because it helps us to understand the other advanced topics that are based upon this simple idealized cycle. Okay, so that's why. So with that, let us start. So uh, just give me 1 minute. Okay, just give me 1 minute. I am so just give me 1 minute. Okay, I'm sorry for the interruption. So let us resume. Okay. So as I was mentioning, like, similar to the cycles that we have seen till now, or in the previous week we saw the Rankine cycle, that was the direct heat engine, right? And in the heat pump or refrigerator, we saw there was a reverse heat engine. Okay, so Carnot cycle is a direct heat engine, like the heat revolves in a clockwise direction. Of course, it does not make any sense, but like, it's not necessary that all of it should move in a clockwise direction in physically, but just for a schematic representation, the working fluid moves in a clockwise direction, or basically it produces work. Okay, it absorbs it produces work. It's a work producing device. Okay, so Carnot cycle is again a direct heat engine, so it exchanges heat through two thermal reservoirs in line with the Kelvin Planck statement, and produces work via a expansion process, and consumes work through a compression process. Okay, so this is the schematic representation of a Carnot cycle. Okay, a heat source, a heat sink, a work producing device, and a work consuming device. Okay, the interesting part arises in how these processes are assumed. Okay, so or materialized, I must say, or how are these process how these processes are achieved. Okay, so this process 1 to 2, that is this heat absorbing process, is in the case of a Carnot cycle, is a isothermal heat addition or an isothermal expansion. Okay, you will see why it's called an expansion when we look into the PV diagram. Okay, then process 2 to 3, that is the expansion process, is essentially the work producing process. So it is a reversible adiabatic expansion. Okay, so first is a isothermal heat addition or isothermal expansion, then the second one is a reversible adiabatic expansion. Okay, then process 3 to 4 is a isothermal heat rejection. Okay, the heat rejection process is again isothermal or isothermal compression, and the fourth process is again a reversible adiabatic compression. Okay, now we have to compress it, so it's a compression process, work consuming process. Okay, I think it's clear. And the important thing to note is that all these processes are again reversible processes. Okay, Carnot cycle is an idealized cycle, so all these processes are reversible processes. Okay, again a much more simpler representation of the Carnot cycle is again this, or Carnot engine is this, that heat consumes heat through a high temperature reservoir, produces work, and rejects the heat to a low temperature reservoir. Okay? A simple direct engine. So this is the TS plot for the Carnot cycle. So for now, I will like to briefly describe it. Again, we have not yet officially, I must say, introduced to entropy. Like we have used it time and time again, and in some equations, but still we have not yet. I don't think we have not yet officially introduced you to entropy. So it won't make much sense for me to right now thoroughly go through this TS plot. Okay, but basically we may understand that in a TS plot, the S is the entropy S is along the x-axis and the temperature is along the y-axis. So this rectangular plot is the representation of a Carnot cycle. Okay, so there is process 1 to 2 is an isothermal heat addition. So isothermal would mean that the temperature is constant. So temperature remains constant here, and then entropy increases. Process 2 to 3 is an isentropic expansion. So the temperature goes down, but the entropy remains constant. Okay, in the expansion process, you will, and then process 3 to 4 is an isothermal heat rejection. So when the heat is rejected, the entropy again goes down. So it goes to S4, or at point 4, entropy just to 0.4, and then process 4 to 1, which was the work consuming device. Sorry, work consuming process is again an isentropic compression. Isentropic would mean that the entropy remains constant, as you can see through these processes 2 to 3 and 4 to 1. Okay, so if we draw the PV diagram, which you are much more quite familiar with, so process 1 to 2, as I mentioned, is a isothermal heat addition or isothermal expansion. So you can see that there is an expansion in the you can see an expansion materialized in the process 1 to 2. The volume, specific volume, increases from 1 to 2, and there is a heat addition. Okay, so if you look for the first law from the first law of thermodynamics, that is Q is equal to du plus PdV. Okay, so considering an ideal gas, so we can write Q is equal to I think, I'm sorry, it should be delta Q. If I'm not wrong, delta Q would be CV dt plus PdV. Okay, so for an isothermal process, dt would be equal to 0, right? Dt would be equal to 0. So we will have, let me move these equations a bit above so I can write the next step. So we will have this delta Q is equal to PdV. Okay, so whatever will be the sign for the work done, the same sign will be for heat addition or rejection, whatever that may be. Okay, so the work and the heat would have, the work interaction and heat interaction would have the same sign. Okay, so since the volume is increasing because it's an expansion process and heat is being added, so in both the cases you can easily see Or you can see another other way, like since the heat addition process, so delta Q is positive, and since pressure, like we are considering Gauss pressure in this absolute pressure in this case, so in that case your P would be positive. Then for this work done to be positive, you need to have this dV change in volume to be positive as well. Then that's why it will basically show an expansion process. Okay, now similarly, let me just distinguish them. 1 to 2 and 3 to 4. This would be 2 to 3 and 4 to 1. Okay. So similarly for now process 2 to 3, that was the isentropic uh, expansion. Let me just see here, reversal adiabatic expansion. So you see that since heat addition is 0, then delta Q is 0 here, right? So we'll have du is equal to minus PdV. So it will mean that the change in internal energy would be like negative of whatever is the change of the sign of dV. So if dV is positive, that is if it's an expansion process, then your internal energy would decrease. Okay, and since internal energy is directly related to temperature in the case of an ideal gas, okay, in the case of an ideal gas, then the temperature will go down. Okay, similarly, that's why the temperature goes down in this expansion process. Okay, temperature goes down. Okay, and there is an expansion from process 2 to 3. Now similarly for process 3 to 4, again we will have it is again isothermal heat rejection. So we go back to here, that is CVDT is equal to 0, so delta Q is equal to PdV. Now since delta Q is negative, P is positive, so dV has to be negative. So for the consistency of the equation, that's why there will be a compression process from 3 to 4. Okay, now with similar argument from process 4 to 1, that is an isentropic or reversible adiabatic compression. So we will have du is equal to minus PdV. Now since dV is negative and we have minus P, so these two has to give you a positive term, because dV is negative here in this case because it's a compression process, right? So dV is negative, it is minus P here, so these both of them should give you a positive term. So internal energy should increase, or basically since for ideal gas du is equal to Cv dt, so since internal energy is increasing, then temperature should also increase. Okay, so this is how you understand your Carnot's cycle. And just for your suggestion, what I can say is that there is a thorough explanation in the thermodynamics textbooks, say by P.K. Nag or this I forgot the author's name, but okay, we can look the textbook by P.K. Nag as well. Like there is a thorough derivation done for evaluating the efficiency of this Carnot engine, okay, or Carnot cycle. So you can go through the derivation. I am not taking it right now, but you can look into that for a better understanding. Okay, that's one homework that you can do. Okay, so I hope this is clear till now. I will give you say 1 minute to just soak in whatever has been discussed till now. Then we can proceed further. Okay. Okay, so we can proceed, I guess. So now comes your Carnot's theorem. Okay, so there are two statements. Let us just go through them once. So there is that no engine can be more efficient than reversible engine operating between the same high temperature and low temperature limit. Okay, so there's the first statement. The second statement is that the efficiencies of all reversible engines operating between the same constant temperature reservoirs are the same irrespective of the nature of the working fluid. The efficiency of the reversible engine depends on the temperatures of the heat source and the heat sink. Okay, so these are the two statements here, and there is a brief discussion about these statements in the following discussion today. But I think you can, like, again, there are different ways to what to say, verify these theorems or prove these theorems. So what you can do is you can again check the textbooks by Pikenak. So this engineering thermodynamics textbook. So there they again look into this, proving these Carnot theorems. Okay, or all these proofs you can look into it. Like it will just be helpful for you in general. Okay. Engineering. I will just write the textbook's name, so it will be better. Engineering Thermodynamics by Pikenak. Okay, so now let us look into the following discussion. So, if I'm not wrong, in the last class I asked you about understanding the correlation between the Kelvin-Planck statement and the Clausius statement. So there is a good proof regarding them, like how the both the statements are correlated with each other. So right now what we will do is a similar exercise, like we will try to see how these Carnot theorems are related to the second law of thermodynamics. Okay, so that's what we are going to do. Again, it's a very simple schematic or logical proof or argument for these statements. Okay, so let us go through them. So consider these two heat engines, one reversible and other irreversible, operating between the same temperature limits. Okay, that is TH and TL. Okay, so the heat engine R represents a reversible heat engine, and heat engine I represents an irreversible heat engine. Okay, so we'll have QH to be the heat input to the reversible heat engine, which will be the same heat input for the irreversible heat engine as well. So heat input is not affected specifically in the case of heat engines. Okay, so whether it is reversible or irreversible, QH is basically your input. Okay, so it doesn't get affected. What gets affected is your work and heat output. Okay, so let W reversible be the work output from the reversible heat engine, and W irreversible be the work output from the irreversible heat engine. Okay, so we'll have QL reversible to be the heat rejected from the reversible heat engine, QL irreversible to be the heat rejected from the irreversible heat engine. Okay, so now consider that if you replace this heat engine by reversible heat engine by reversible heat pump, okay, so it will now operate in the reverse direction. Okay, sorry for this disturbance. Just give me 1 second. So yeah, so if you replace this reversible heat engine by reversible heat pump, so the direction of the heat transfer will get reversed. Okay, so the irreversible heat engine is unaffected, but we're replacing by the heat engine by a heat pump. Okay, so so now instead of QH being the heat given to the reversible heat engine, QH is the heat rejected out of your heat pump. Okay, and QL reversible is the heat input or heat absorbed from the low temperature reservoir, and W reversible is the work input to the reversible heat pump. Okay, so I am speaking very slowly and clearly, so I think the arguments or these discussions are quite well understood. Okay, so I assume that I am speaking clearly enough for you to understand it clearly. It's quite simple, not that difficult, but important to understand. That's why I'm just trying to speak very, very slowly. So if you now apply the first law of thermodynamics for this reversible heat pump, you will have QH is equal to QL reversible plus W reversible. Okay, I will not go through the detailed discussion, but it is what you will get considering the sign convention that we have discussed. Similarly, for the irreversible heat engine, for it gives us a cyclic process, both of them. Okay, both of them gives a cyclic process. So you will have QH is equal to W irreversible plus QL irreversible. Okay. So now let us assume that this is an assumption that W irreversible is greater than W reversible. Okay, so this discussion clearly violates your Carnot's theorem, saying that the reversible cycle is more efficient than your reversible cycle. The reversible cycle is more efficient than the reversible cycle, so it is producing more work. Okay, so it's a clear violation of the Carnot's theorem. Now, if you implement this in these equations, so you will clearly see that this will give you QL reversible to be less than QL irreversible. Okay, after you consider this assumption. Okay, so these things I hope you are following, so that's fine. So now what you can consider is that now since QH is the heat rejected out of the reversible heat pump and QH is the heat now absorbed by the irreversible heat engine to operate, so what we can do is now let us just bypass this thermal heat reservoir, right? There is no point of having this, because what we can do is we can directly just draw it. It will be much more clearer then. Like rather than having this thermal reservoir, what we can do is we can connect this heat rejected out of this heat pump to be the heat input to the irreversible heat engine, right? We can clearly bypass the thermal reservoir. Okay, so now if we do that, you can see that this would be the simplified version of this cycle here. Okay, so the reversible heat engine operates, absorbs QL reversible from the lower temperature reservoir, rejects the work, the heat QH, and this is the heat input to your irreversible heat engine. So what happens is that since this irreversible heat engine produces a work W irreversible, and this reversible heat engine absorbs a work W reversible, and from the assumption that we have taken here initially by violating the Carnot's theorem that W irreversible is greater than W reversible, then basically the work from the irreversible heat engine is greater than the work absorbed by your reversible heat pump. So basically it is generating an excess work, that is W irreversible minus W reversible. So this is positive given that this is valid. Okay, so if that's the case, then we can use this excess work as a work input to operate this reversible heat pump. So if that's the case, now we can consider this entire thing to be a single unit. So basically what would happen is that also here also, if you see, you can basically see that this structure or this setup is basically absorbing heat from the or exchanging heat from a lower temperature reservoir and producing a work, this W excess. Okay, so basically this setup is acting as a heat engine by absorbing heat or interacting with a single heat reservoir and producing an excess work W excess, which is the clear violation of your Kelvin-Planck statement. So because if the Carnot theorem is not valid, or this is the case, then Kelvin-Planck statement is violated. That's why for any temperature limit, Carnot's engine must be the most efficient engine. Okay, that's why Carnot engine is the most efficient heat engine working within the same temperature limit. Okay, so that's how your Carnot's theorem or it is justified. Okay, I hope this is clear till now. What I will do is I will zoom out a bit, show you the diagram here. You can just briefly go through them once. Meanwhile, I will also take a rest for 1 minute and then we can again resume our discussion. Okay. Then you go to a diagram. You can draw the try to understand what's happening and then you can resume. So I think then we can proceed further. Okay. Now comes a basic derivation or discussion on the absolute temperature scale, or more specifically the relation of how the efficiencies of this reversible heat engines are determined. Okay, so if you recall, you may recall that in the previous classes we have said that for reversible heat engines, the efficiencies of reversible heat engines are given by 1 minus TL by TH. But in general, efficiencies of heat engines are given by 1 minus QL by QH. So this is the generalized case, but this is the specific case for reversible heat engines. Okay, and I mentioned that uh, there is a foolproof discussion on how we are able to derive this, and we will use a similar argument to show why this is the case for reversible heat engines. Okay, in this discussion, but for a more detailed understanding, again you can prefer any standard thermodynamics textbooks. Okay, so just give me 1 second. Okay, I'm just trying to see. Yeah, thermodynamics textbook by Sengel and Bowles. Okay, Sengel and that's the textbook. Again you can also that's again the textbook you can prefer. Okay, it's a very theory heavy textbook. Like the numerical these problems are not that much, but for understanding the theory, all the discussion that I have done here, it's done very nicely in this textbook. Okay, Sanger and Bowles. It's again a very good textbook. I missed out this textbook or referring to this textbook when I was in my bachelor's, but maybe that's why I didn't have that clear cut grasp on the subject of thermodynamics and was not able to cherish the beauty of this subject. But for you beginners, like if you are just starting this thermodynamics course from this NPTEL's course, like then you can follow this textbook. It's a very good textbook. It will help you to what to say, strengthen your concepts on thermodynamics. Not only in thermodynamics, but in these thermal sciences in general. Okay, say thermodynamics, heat transfer, fluid mechanics. So they try to correlate all these things and try to put it in a way that we are able to correlate these different concepts together. That's why I think this book is much more suitable in a way when you're trying to understand the concepts in a much better way. And this is what actually how study should be done. Okay, any course has to be studied. Okay, so that's why I will suggest this textbook, but you can just see once if you are finding it suitable. Okay. So the absolute temperature scale, the argument is that the temperature scale is independent from the working substance. Okay. So let us consider the following diagram. That is three thermal reservoirs. Okay. T1, T2, T3, and with three heat engines, where A is the heat engine operating between T1 and T2, B is the heat engine operating between T2 and T3, and C is a heat engine that operates between T1 and T3. Okay, and Q1, Q2, Q2, Q3, Q1, Q3 are respective heat interactions of these heat engines as shown in the diagram. I think it's quite well understood. And WA, WB, and WC is the net work produced from these three heat engines. Okay. So the schematic setup of the heat engines are quite clear. I think now we can proceed. So we'll have, let's consider this first heat engine that operates between these two temperature limits. So we'll have WC is equal to Q1 minus Q3 from the first law of thermodynamics. Okay. Eta, or efficiency of this heat engine, would be W by Q1, or eta would be Q1 minus Q3 by Q1, or eta is 1 minus Q3 by Q1. Okay. And our argument is that this Q3 by Q1 has to be a function of T1 and T3. Okay. What is this T1 and T3? What the function of T1 and T3 is not yet proved, but the argument is that the ratio of this Q3 and Q1 has to be a function of temperatures T1 and T3. Okay. So that's the argument. Okay. So we know that the efficiency of a Carnot engine is 1 minus QL by QH, which is a function of TL by TH. Okay, like if these are Carnot engines, okay, this A, B, and C, then this efficiency is basically a function of the ratio of temperature TL by TH. Okay, so we'll have that Q1 by Q2 is a function of T1 by T2, and Q2 by Q3 is a function of T2 by T3. Q1 by Q3 is a function of T1 and T3. Okay, so a simplified what to say, assumption again would be that this, instead of these three functions being three separate functions, we can consider that these functions are a common function f, which is a respective function of the temperature limits between which these heat engines are operating. Okay, so the heat ratios, that is Q1 and Q2, or this high temperature and low temperature heat ratios, are a function of this high temperature and low temperature limits between which these heat engines are being operated. Okay, that's an assumption that we take. Now this Q1 and Q3 would be a function of T1 and T3. So we can write Q1 and Q3 as Q1 by Q2 times Q2 by Q3. Okay, so this times this, or function of T1 comma T2 times function of T2 and T3. Okay. Now the argument is that for Q1 and Q3 to be function of T1 and T3 only, the only way, okay, or the most simplified way through which this can only be a function of T1 and T3 is that if this f of T1 and T2 is a ratio of some function of temperature T1 by T2, and f of T2 by T2 and T3 is f of T2 by T3. So in that case, if that's the case, then we can easily neglect out this or cancel out this f function of T2 from the numerator and denominator, and we will have that function T1 or function of T1 and T3 is function of T1 by T3. So that's the only way we can have this Q1 by Q3 to be a function of T1 and T3 only. Okay, so we get our result that the heat ratios should be equal to should be the ratio of these functions of the temperature limits, that is the the temperature limits between which these heat engines are being operated. So Q1 by Q3 should be the ratios of function of T1 and function of T3. Okay, so that's what we have reached till now. And what Kelvin's assumption was that this function of T1 and T3 is nothing but the ratio of T1 and T3 itself. So according to Kelvin's assumption, he says that for reversible heat engines, again for reversible heat engines only, Q1, or basically the ratios of the high and low temperature, or the ratios of the this high and low heat transfer is actually the ratio of the high and low temperature limits between which the heat engine is being operated, or the heat pump is being operated. Okay, so that's what Kelvin's assumption was. Okay, for reversible cycles. Again, for your better understanding, or if you want to know more, there would be again a thorough discussion on how this is being done. This is exactly what I asked you to do. You can just research it in your own, from your own end, like how the Kelvin assumption was made, how these assumptions that have been taken to derive this are done. You can what you can do, you can try to look it out in the standard textbooks, or refer to the sources that they have mentioned. Okay, so through that you can easily understand how this is, or you'll be able to appreciate like how these discussions are being made. Okay, so that's something that you can do from your own end. Okay, so now let us take some examples. An engine works on a Carnot cycle and it rejects 30% of the heat it absorbed from the source. The sink is at 25 degrees Celsius. Calculate the source temperature. Okay, so this is an example taken by Professor Anand in the lecture, so I'm just going to go through it once. But if you have any doubt, or if you want to solve this question by yourself while watching the recordings, you may pause the video right now, try to solve it out, and then you can play it again to compare your results. Okay, but for sake of saving time, I will start to discuss it right away. Okay, so QL is 0.3 times QH as discussed here. It rejects 30% of the 30% of heat absorbed from the source. So QL is 0.3, 30% of QH. TL is 100 degrees Celsius, that is 298 Kelvin. You need to find out TH. Okay, so for a Carnot engine, which is a reversible heat engine, from the Kelvin's assumption we have that QL by QH should be equal to TL by TH. Okay, if that's the case, then TH is QH by QL times TL, or QH by QL is 1 by 0.3 times 298, or 993.3 Kelvin. Other way around is to find the efficiency directly, then find the temperatures from there. Like you can do something like 1 minus QH, sorry, 1 minus, I'm sorry, 1 minus QL by QH should be equal to 1 minus TL by TH. Again, this will directly give you, if you do it, you will get the same result. Okay, so you can do it like that. It's your choice. So the next question is, a heat engine operates between a hot reservoir at 500 Kelvin and a cold reservoir at 300 Kelvin. If the heat engine absorbs 3500 joules and rejects 2500 joules of heat, calculate the work done, efficiency, and the maximum possible efficiency. Okay, so you may ask why these two efficiencies are mentioned. So let me tell you. In general, it is not mentioned that it is a reversible heat engine. Okay, so it's just the temperature limits are given, and the ratios of, and the heat absorbed and the heat rejected are given. Okay, so in general, for any heat engine, be it reversible or irreversible, the efficiency eta is given as 1 minus QL by QH. That's a universal law. Okay, so no case of reversibility, irreversibility is considered here. That's a generalized case. But because we know that if the cycles or a engine operate between the same temperature limits, then the Carnot engine, or I must say a reversible heat engine, would have the highest possible efficiency. And we know that the efficiency of these reversible cycles are given by 1 minus TL by TH. Okay, so that's the case. So with that argument, we can see that so work done can be easily found out from the first law, that is W net is QH minus QL, or 2500 minus 2500, or 1000 joules. Okay. Then efficiency eta is W net by QH, or 1000 by 3500, or it is equal to 28.57 or 28 0.257 or 28.57%. Okay, just give me 1 second. So for maximum efficiency, as I mentioned, the maximum efficiency for an engine operating between the same temperature limits would be a reversible heat engine. So the Carnot efficiency. So we'll have either Carnot be 1 minus TL by TH, or 1 minus TN by 500, or 0.4. So you can clearly see this Carnot efficiency is higher than the normal efficiency or generalized efficiency for this heat engine. Okay. So now comes again one of the important discussions on the second law of thermodynamics, that is your Clausius inequality. Okay. Again, it is one way or another graded quite what to say thoroughly related to Carnot theorems. So you will see how this conceptualized here, but it's important for you to as well to understand this correlation. Okay. So as you can see till now, like we saw that the Kelvin-Planck statement and the Clausius statement are related to each other. Of course, this is homework to you. You can do that and try to derive the what to say, the correlation between your Kelvin-Planck statement and the Clausius statement. That's the second law. We again saw that your Carnot's theorem is again related to your what to say, the Kelvin-Planck statement. So justifying that is another way to understand, or what to say, simply understand the second of thermodynamics. We'll again see that this Clausius inequality, or this discussion, is again one of the, I must say, one of the outcomes of the Carnot's theorem. So you can say all these discussions are one way or another related to the understanding of the second law of thermodynamics. Okay. So yeah, let us just go through it. Maybe after discussion you will be able to understand or appreciate the beauty of this second law, okay, in a much better way, because all these discussions are one way or another just going back to the basic statement of the second law. So this is a reversible heat engine as shown in this diagram. Okay. A high temperature reservoir, low temperature reservoir, a heat engine, direct heat engine operating between these two temperature limits, absorbing heat QH, rejecting heat QL, and producing a net work W. So from the Clausius inequality, for a reversible heat engine, we will have QH by TH is equal to QL by TL, like from this discussion. Okay, so this, if you rearrange in a way, you will get QH by TH is equal to QL by TL. Okay, that's first statement that you need to know. The Clausius inequality states that this cyclic integral of del Q by T is less than or equal to 0. This is the Clausius statement of the Clausius inequality. Okay. Now for a reversible heat engine undergoing a cyclic process, we have the cyclic integral of del Q by T. This is del Q by T reversible. We will have QH by TH plus QL by TL. So QH by TH is positive because both TH and TL, like, since it should be greater than the absolute zero temperature, and TH and TL are in the absolute temperature scale, so TH and TL are positive. So the only thing that determines the sign of this ratio is the sign of this heat transfer. So QH is positive because it is heat added to the system, that is the Carnot engine in this reversible heat engine in this case, and QL is the heat rejected out of this reversible heat engine. So this is negative. So if you consider the signs, you will get that Since QH by TH is equal to QL by TL from your statement, from the Kelvin's assumption, that's why if you substitute QH by TH is equal to QL by TL in this equation, you will get this summation of del Q by T reversible for a reversible engine to be equal to 0, which is exactly what which you will eventually see. I'm sorry, like this inequality is basically like it's equal to 0 for reversible processes and less than 0 for irreversible processes. That's why I wanted to show, but I just told you beforehand. Yeah. So as you can see, for reversible process, this summation of del Q by T is equal to 0. Like just trying to correlate the definition of process or the equation for process inequality and your Kelvin's assumption or Carnot's theorem. Okay, that's the first thing. Second is, now let us consider it for a heat pump. Okay, similarly we will have for a reversible heat pump, del Q by T reversible would be QH by TH plus QL by TL. QH is negative in this case and QL will be positive. Again, from this Kelvin's assumption, you can show that this would be equal to 0. So this cyclic integral of del Q by T is for reversible process is equal to 0 for both heat pumps and heat engines. Okay, this is a heat pump as shown here. So now consider this following diagram. Okay, now let us try to see the same case for an irreversible cycle. Okay, the first cycle here is again a reversible heat engine as shown here. The second cycle, as you can see here, is an irreversible cycle where QH is again the same, but the work done and where the work done and the heat rejected are being affected because of the irreversibilities in the heat engine. So from the Carnot's theorem, which says that the reversible heat engines are the most efficient heat engines operating within the same temperature limits. Again, these two are equal. These temperatures are equal to each other and these are equal to each other. Then only this statement works. Okay, the Carnot's theorem is valid. So work done, or since the reversible heat engines are the most efficient heat engines, so the work produced from a reversible heat engine has to be greater than the work produced from an irreversible heat engine operating between the same temperature limits. So from the first law, you can clearly prove that if this is the case, then from the first law we will get that QL, there is a heat rejected out of your reversible heat engine, is always lower than the heat rejected out of the irreversible heat engine. Okay, so from the Clausius inequality we will have QH by TH plus QL by TL equal to 0 for a reversible heat engine. Okay, or if you take the modulus, like because QL is negative in the case of heat engine, we will have QH by TH minus QL by TL equal to 0 for a reversible case. Okay, reversible heat engine. Reversible heat engine. Now, if we consider irreversible case, you can replace this QL by QL irreversible, and you will see that since QL reversible, the magnitude of QL reversible is greater than QL, then QH by TH minus QL irreversible by TL would be less than 0, right? Again, I'm sorry. I hope it is visible again. I'm sorry. Okay. Yeah. So with this argument, you can clearly show that this QH by TH minus QL reversible by TL will be less than 0 because the magnitude of QL reversible is greater than QL. Okay. So now you can say that the cyclic integral of del Q by T, that is QH by TH plus QL reversible by TL, is less than 0 for an irreversible cycle. Okay. So what we get is that for reversible cycles we have cyclic integral of del Q by T to be equal to 0, and for irreversible cycles we have cyclic integral of del Q by T to be less than 0. And this is exactly what the Clausius inequality means. Okay. Now let us look into this term itself. What this del q by t actually means. Okay, what does it signify? Now consider this diagram. This is a basic PV plot showing three separate processes. That is, it goes from state point 1 to state point 2 through different paths A, B and C. Now from process inequality, we know that this del q by t for reversal process is equal to 0. So if we consider all these three paths to be reversible paths, so we'll have for path 1a to b1, we will have del q by t to be equal to 0, or from 1 to 2 del q by a by ta, so del q a by ta, plus from process 2 to 1 to part b, that would be del q b by tb to be equal to 0 from process inequality. Okay. Similarly, if we consider the part 1a to c1, this part you will have del q by t equal to 0 from the process inequality, or from 1 to 2, for integral from 1 to 2 del q a by ta, plus integral from 2 to 1 del q c by tc to be equal to 0 from the process inequality. Now since these two terms are same, if we equate it, you will see that from process 2 to 1 del qb by tb is equal to process process 2 to 1 you will see that this ratio of del qb by tb and integrated from 2 to 1 is equal to del qc by tc integrated from 2 to 1. Okay, so this entity, that is del q by t, is actually equal for a reversible process across any paths. So basically it shows that this process, or this entity, this integral from 1 to f, or this del q by t, is essentially a state function because it's independent of path. Okay, for reversal process this is independent of path, that's why it is a state function. So if you recall, like we had similar arguments in the first law, that del q minus del w, that is d, is a property of the system. So the first law gave us one of the properties of the system, that was the energy of the system. Okay, similarly the second law gives us another property of the system known as the entropy. The entropy of the system, where entropy is defined as del q by t for a reversible process. Okay, or the ratio of the heat transferred over the temperature at which the heat is being transferred for a reversible process is known as the entropy change, or net entropy change, or in which this entropy or entropy change is the property of the system. Okay, so for a reversible process, okay, again for a reversible process only, we can say that the integral of del q by t for reversible process is equal to the net change in the entropy. Okay, as mentioned here, and this is where we formally introduce or define the term entropy in this course. Okay, so entropy, like in general, like if you had studied in class 11, 12, or even in your batches as well, the term is usually what to say, related to the degree of randomness in the system. Like in general as well, like if once somebody says that what is entropy, is the measure of the degree of randomness in the system. Okay, and the second of thermodynamics in general may be said as then the entropy of the system or entropy of the universe always goes on increasing, or the degree of randomness in the universe goes on increasing. Okay, so right now you may not be able to correlate these two statements. Okay, the degree of randomness and this very what to say, plain looking definition, you may not be able to correlate them together, or you will not be able to correlate the statements of that is the degree of randomness of the universe goes on increasing as the second of thermodynamics, and the Kelvin Planck and the Kelvin Planck statement and the process statement. You will not be able to correlate these three statements all together. Okay, but eventually when we are when we complete this course, or you are referring to textbooks that we have suggested you will eventually be able to understand like how these statements or how these concepts are so strongly correlated to each other. Okay, how the degree of randomness of the system is related to this simple looking, plain looking statement. Okay, it may not seem quite obvious now, but you will eventually be able to appreciate it once you are able to, what to say, completely understand the course. Okay, or at least you have completed the course and are quite well versed with the topics that have been discussed. Okay, so that's the end goal, but of course there is a learning curve, and we expect I hope that once the course is completed, you are able to understand this in at least in a much more better way than you are understood it before attending this course. Okay, so as I mentioned here, that in classical thermodynamics, the entropy can be defined as the ratio of heat transferred to the temperature at which it is being transferred. Okay, and we see that it is a state function for a, and is defined for a reversible process only. Okay, as a state function, then delta S for part B, that is it's an irreversible process as shown in this curve, would be delta S reversible as calculated for path A. Okay, so delta S for B is not equal to cyclic integral of del Q B by TB, because this is not defined for a irreversible process. Okay, that's why integral of del Q B by TB for irreversible process is not equal to delta S. If you want to know delta S between point 1 and 2, what you can do is you can calculate this delta S for reversible part, say across a part A, and then find the change in entropy from 1 to 2. Okay, so this thing right now, I do not think that you will be able to understand it in the most clearest possible way, but it is something that for now what you can just take this as a statement or take this for granted right now. But eventually when we discuss about entropy generation, hopefully in the next class, then you will be able to understand like why this argument is very very important. Okay, like calculating the change in entropy through an irreversible path or irreversible process to the change in entropy through a reversible path. How we are able to correlate them, you will eventually see. Okay. Now, Professor Anand also briefly introduces or states the third law of thermodynamics here, that for an absolute zero temperature, the entropy of that in that case is equal to 0. Okay. Now let us look into the property relations or thermodynamic property relations, which let us see how they are derived. It's very important. So let us go through the equations once. Okay. So after that, I think after the equations, we will directly start the problem solving part. So then we can look into it. Okay. So let us try to derive these thermodynamic property relations, and then let's proceed further. Okay. From the first law, we have that dE is equal to del Q minus del W. Okay. Now, or del Q is equal to dE plus del W. Now, for simple compressible substances, energy would be written as U plus K plus P. Okay. Considering K and P to be negligible and considering only shaft work, we can write TdS is equal to du plus PdV. Okay. Again, this del Q to be equal to TdS, that comes from ds is equal to del Q by T, is only valid for reversible processes. Similarly, del W is equal to PdV is only valid for reversible processes. Okay. So the equation derived till here. Okay. So you may argue that this argument is valid for reversible processes only. So the equation that we get is TdS equal to du plus PdV, or say if you want to write, I guess it's already in small sign. Okay. That is, this ds is the specific entropy, du is the specific internal energy, and dV is the specific volume. Okay. Similarly, we know that H is equal to U plus PV, that is enthalpy. dH is equal to du plus PdV plus VdP. Okay, again all these are small letters, so these all are specific quantities. There is properties per unit mass. Sorry. Then from this equation we'll have that du plus pdv is equal to tds. Okay, in this equation, so you can write tds is equal to dh minus vdp. Okay, these equations are known as the thermodynamic property relations or the Gibbs relations. Okay, and since these equations relate only the thermodynamic properties, okay, that is the temperature, entropy, in specific internal energy, specific volume, specific enthalpy, that's, and pressure as well. Pressure is again a thermodynamic property. So these Gibbs relations are valid for any kind of processes. Okay, that's something again. It's maybe hard to digest at first. So, but if you see to the equations, you'll understand why this becomes valid for all kinds of processes. Okay, so these Gibbs relations or these thermodynamic property relations are valid for all processes. Okay, irrespective of them being reversible or irreversible, primarily because these relations are correlating these thermodynamic properties and not these path functions. Okay, that is such as heat and work done. They are correlating temperature, entropy, temperature, specific entropy, specific internal energy, pressure, specific volume, and specific enthalpy. Okay, these all are intrinsic properties or path independent properties or thermodynamic properties. That's why these equations are valid for any kind of processes. Okay, now for solids and liquids, these equations are modified a bit, primarily because the change in a specific volume in the case of solids and liquids are very small or almost negligible. That's why TdS becomes equal to du or cv dt, or ds becomes equal to cv dt by t. If we integrate it, delta s becomes integration of cv dt from cv dt by t from 1 to 2, or cv natural log of times natural log of t2 by t1 for solids and liquids. Now for ideal gas, you have TdS is equal to du plus pdv, or TdS is equal to cv dt plus pdv, or ds is equal to cv dt by t plus p by t times dv. So the goal would be, since we have a ratio of dt by t here, we want something in terms of volume, so then we can when we integrate, we can get the change in volume as well. Okay, and since these two are changing, so we cannot integrate it together. We want something like, since dv is the property that is changing, we want volume as well as a property that is independent, or I must say independent of the integration, like it's a constant. So we, from the ideal gas law, we have PV is equal to RT, or P by T is equal to R by V. Okay, so we have P by T is equal to R by V. So if you substitute P by T is equal to R by V in this equation, you will get ds is equal to cv dt by t plus R by V times dv. Now if you integrate this equation, you will get delta S is equal to cv times ln t2 by t1 plus R times ln v2 by v1, for cv is equal to constant for a calorically perfect gas. Okay, so this, if you go back, this equation is valid for any kind of process and for any kind of substance, but these are again the specific cases. This is for solids and liquids, and this is for an ideal gas. Okay, similarly, we have TdS equal to dH minus vdp, or ds is equal to dH by t minus v by t times dp, or ds is equal to dH by t. Now v by t, when we want something in terms of pressure, so we have v by t would be equal to R by P again. So ds equal to Cp dt by t minus R by P times dp. Now if we integrate it, we will have delta S equal to Cp times ln t2 by t1 minus R times ln p2 by p1, for Cp equal to constant. Okay, so now for reversible, we saw that del W is equal to pdv was, we saw that this integration under this pdv plot, that is pdv plot, the area under the pdv plot gives the work done for a reversible process. Similarly, we have delta S or ds is equal to del q by t for reversible process, or in specific terms or specific properties, we have ds is equal to del q reversible by t, or del q reversible is equal to tds. So for a reversible process, the area under the ts plot gives us the net heat transfer. Okay, so now you know what the area under ts plot gives us. Okay, so now we can easily talk in terms of ts plots as well. Okay. So I think that's all for the theory part for today's discussion. So now I think we can start with the uh, question answer part. So let us look. Okay. So from this, just give me 1 second. Yeah. Which one of the following is the correct expression for Clausius inequality? Okay. So since there are less students in today's class, what I will say is again, I will you can I will directly start discussing the solution. Okay, but for now, what you can do is you can, if you want to solve it yourself, you can take as much time as you want while you are looking into the while you are looking the video. You can pause the video right away, try to understand or find a solution, and then you can resume the video to compare the results. So in this case, the Clausius inequality right now we have just discussed, so it is given by b, that is cyclic integral of del q by t is less than or equal to 0. Okay. Which of the following is or are not a correct statement or statements? Okay. Clausius inequality is valid for reversible cycles only. Clausius inequality is valid for irreversible cycles. Clausius cycle is not valid for refrigeration cycles. Clausius inequality is valid for irreversible cycles only. Okay. So which is or which are the or which are not the correct statements? So you can pause the video now. So answers I can say now. So answers would be Clausius inequality is valid for all cycles. So this statement is incorrect. That is valid for reversible cycles only. So this is incorrect. Clausius inequality is valid for irreversible cycles. Yes, it is valid for irreversible cycles. Clausius inequality is not valid for refrigeration cycles. Is not the case. It is valid for refrigeration cycles. So this is again wrong. Clausius inequality is valid for irreversible cycles only. Again, this is not the case. Clausius inequality is valid for reversible cycles as well. So A, C, and D are incorrect. Okay. So let us look into question number 3. A block of mass 12 kg and average specific heat of 3 kilojoule per kg degree Celsius is cooled from 35 degrees Celsius to 5 degrees Celsius. The entropy change of the block is, okay. So you can pause the video now. Okay. I will discuss the solution. So you may try to find the solution of the question by yourself after pausing the video, and then you can play it again to see whether the answer is matching or not. Okay. Sounds good. Then I think we can proceed. So we have mass of the block is 12 kg, CV or specific heat at constant volume is 3 kilojoule per kg degree Celsius, and the initial temperature is 35 degrees Celsius, and the final temperature is 5 degrees Celsius. This is basically being cooled. So one more thing that you can see, is now that del Q reversible is equal to TdS. So if del Q is negative, ds will be negative. Change in entropy will be negative, because temperature, like from this equation, like if temperature is positive for an in absolute temperature scale, temperature will always be positive. If it's 0, then everything will be 0, right? Change in entropy will also be 0. Okay. So T has to be positive. So if del Q reversible is negative, that is if the object loses heat, then ds will also be negative. So it is something that you can check before, like once you get the solution, whether this is making sense or not. Okay, so we will have delta S for a solid block. Since there is no change in the specific volume, the volume change part is 0. So we have delta S equal to m CV ln Tf by Ti. Okay, m is 12, CV is 3. Be consistent in units as well, and natural log of Tf by Ti, and Tf and Ti should also always be in the absolute temperature scale, that is in terms of Kelvin. If you do that, you will get delta S as 3.689 kilojoule per degree Celsius, okay, or 3689 joules per degree Celsius. Okay, and this degree Celsius is from the very unit here. Okay, so don't get confused with that. It is why it's not in Kelvin. Okay, you can write in Kelvin as well, no problem. But since this initial unit was in degree Celsius, so it is keeping that similar thing. next question. Yes. Water flows through a turbine in which the friction causes the water temperature to rise from 35 degrees Celsius to 37 degrees Celsius. Okay, friction from the water causes uh, the temperature to rise from 35 degrees Celsius to 37 degrees Celsius. If there is no heat transfer, how much does the entropy of the water change in passing through a turbine? Okay, entropy change when passing through a turbine. Water is incompressible and the process can be taken to be at constant volume. So you will have uh, del V equal to 0 and CV is equal to constant. So this is something you need to take. Okay. So you can pause the video now. I will discuss the solution. So important point the important point here to note is that the presence of friction makes the process irreversible and causes the entropy increase in the system. Now, since the entropy is a state property and the entropy change depends on the two end states and is independent of the path the system follows, we can find the entropy change for the irreversible part. We can irreversible part by replacing irreversible part by a reversible part, as discussed in the previous argument, like when we were discussing about this. If I go back, like this one, like finding the entropy change from 1 to 2 through a reversible part for an irreversible process. Okay, okay. So you will see how that you will see that in action now. Okay, so we have T1 or T initial as 308 Kelvin and T2 is increased because of friction. The temperature is 310 Kelvin, and del Q reversible is equal to TdS. Now ds is equal to mcv dt by t. Okay, or if you integrate it, you will get S2 minus S1 is equal to mcv ln T2 by T1. So the change in entropy through this reversible part would be given by this relation. Okay, now mass is per kg, right? We are asked to find the change in entropy. If I go back to the question, let me just look into it. So let us find so let us find for per kg of water. Okay, so since not mentioned, so you can do it for per kg of water. Okay, so you'll have S2 minus S1 as mcv ln T2 by T1. M is 1, Cv is 4.17 for water, and natural log of T final temperature is 310 and initial temperature is 308. Now you can see that since the friction causes the temperature of water to rise up, heat is being transported into the system. Okay, there's no additional heat addition through any other external heat source, but the heat addition or heat is being absorbed in the system because of the frictional effects. That's why the temperature increases. Okay, so if that's the case, then the entropy will also increase. Okay, so you'll see that the change in entropy turns out to be 0.0271 kilojoule per Kelvin. Okay, again, see, this is positive, so it shows that the entropy is increased because of this friction caused due to the water when it flows through the turbine. Okay, so let us look into the next question. Okay, I hope this is clear till now. If it's confusing, again, I think this might be confusing, that is calculating the entropy for an irreversible process via reversing it by a reversible part. So I think it will be much more clearer when we discuss about entropy generation and the total entropy for a universe. When we discuss about those things, it will become a bit more clearer. But till then, I think you can just help me out as well by bearing with it and taking this argument for granted, right? Just for right now. Okay. So next question is, a body of constant heat capacity Cp, just write it Cp, and the initial temperature of T1 is placed in contact with a heat reservoir at temperature T2, and comes to a thermal equilibrium with it. Okay, so when a body is in contact with a thermal energy reservoir and whose initial temperature is T1 and the temperature reservoir is T2, which is greater than T1. So basically the reservoir and the body is exchanging heat with each other till they reach a thermal equilibrium. Okay, so basically since the body is at a temperature lower than the reservoir, so it will gain heat, and the reservoir, since it is having a finite temperature, it will lose heat. Okay, because they are coming in equilibrium. So if it would have been an infinitely large thermal reservoir, then the temperature would have remained constant. But it is saying that they come into a thermal equilibrium, so means that the temperature of the reservoir is a finite temperature reservoir, so it should also, the temperature of the thermal reservoir should also go down for the equilibrium to be achieved. So it is given that T2 is greater than T1. So calculate the entropy change of the universe and show that this is always positive. So delta S universe is basically your delta S universe is delta S system plus delta S surrounding, or in one way, like summation of the change. If you consider surrounding to be another system, because here, like if you consider this body to be only be interacting with your thermal reservoir, then the surrounding to the body would be your thermal reservoir. So basically the surrounding change in the delta S surrounding would be the change in the entropy of your thermal energy reservoir. Okay, so this change in the entropy of the surrounding can be considered as another system that is interacting or with the initial system, this is system 1, and the change in the entropy of all the systems that are interacting with each other would give you the change in the entropy of the universe. Okay, so we have to show that it is always positive. Okay, so with that idea in mind, let us try to look into it. Okay, so you can again pause the video right away. Pause the video for here, and I'll start discussing the solution now. Okay, so the change in the entropy of the body is given by integration of MCP, integration of dt by t, integrated from t1 by t1 from t1 to t2. If you go back to the question, let me just go back to it. It's mentioned that it's a constant heat capacity and it's a body. Okay, so in essence it states that it's either a solid or liquid. In that case, the change in the specific volume is negligible, so this change in the volume part would be disregarded. So we'll have this to consider your change in the total entropy of the body. Okay, this part. So here you need to consider this MCP at constant pressure. Okay, so if it is at constant volume, you can take CV, but in the question it specifically mentions CP, so you can start with that. Okay, and the delta S of the surrounding would be minus of MCP T1 minus T2 divided by T2. Why? Because see, let me just draw a diagram that will make much more sense, I guess. So there is a body here. This is the body, and say this is the object, and this is the reservoir. Okay, this is a temperature. The reservoir is a temperature T1, and the object is a temperature T1, and the reservoir is a temperature T2. And the heat is being transferred from the reservoir to the object. Okay, and the heat transferred from the reservoir to the object would be in this direction because it is at high temperature, right? So naturally heat will go in this direction. Then what we will have is that this change in the entropy of your reservoir would be del Q by T2, right? So we'll have the magnitude of this heat transfer would be MCP T1 minus T2. Why? Because T1 is greater, so magnitude is T1 minus T2 divided by T2, but Since the heat is being rejected out of the system, so it will be, of the reservoir in this case, will be negative. So this is what been shown here. Okay, so we can write this delta S universe. Let me just write that as well for your reference. Delta S universe would be delta S system plus delta S reservoir. Okay, or to be much more clearer or in line with the arguments, that delta S body plus delta S reservoir. Okay, so we can take this MCP common. Okay, so we'll have natural log of T2 by T1 minus 1 minus T1 by T2. Now let us, if we take 1 minus T1 by T2 as a term x, so we will get T2 by T1 as 1 minus 1 by x. Okay, since T2 by T1 is greater than 1, because T2 is greater than T1 as mentioned in the question, we just write it as well, and here T2 is greater than T1. So because that's the case, then we can write this delta S universe by MCP to be equal to minus of natural log of 1 minus x minus x. Okay, why? Because see, this, if we just write it here, like here, it will be delta S universe to be equal to MCP natural log of 1 by 1 minus x minus x. So natural log of, so we can write this one as, sorry, MCP. So if you want to reverse, like put the numerator to the denominator, denominator to numerator, like if you try to take the inverse of the argument of the natural log, so it will become minus of 1 minus x. Okay, basically 1 minus x divided by 1 minus x. So that is, or delta S universe is MCP equal to minus ln 1 minus x minus x. Okay, and then if you try to take the Taylor series expansion of your this function natural log of 1 minus x, you can just Google it, or just, if you know, that's much better. But if you Google it and try to see it, you will get that there will be an x term here plus x squared by 2 plus x cubed by 3 by x cubed by 4 plus dot 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 to infinity minus x. These two x will get cancelled out, so we will left with delta S universe to be x squared by 2 plus x cubed by 3 plus x squared by 4. And since this 1 minus T1 by T2 is always positive, therefore this term is always positive, so delta S universe is always positive. Okay, that's what we have proved here. So let's look in the next question then. I hope it is clear. If there's any doubt in the solution, of course you can put that in the discussion forum or in the comments of this video as well. Okay, after you receive the recording. Just give me 1 second. Question number 6. Okay. A fluid undergoes a reversible adiabatic compression from 0.5 megapascal and 0.2 meter cube to 0.05 meter cube according to the law PV through 1 by 3 is equal to constant. Determine the change in the enthalpy entropy and the heat transfer and the work transfer during the process. Okay, so enthalpy, internal energy, entropy, heat transfer, I think it's not that difficult, because you are given the initial pressure, initial volume, final volume, and also the PV relation. If you do that, you can pause the video now. I will solve the solution, so you can just try to you can see how you'll do that. Okay, you pause the video now and discuss the solution. So we know that TdS is equal to Ts minus VdP as from the thermodynamic property relations or the Gibbs relation. Now, since it's a reversible adiabatic process, okay, the question, it is a reversible adiabatic process. Okay, this one. Therefore, we have dH is equal to VdP. Okay, P1 is equal to 0.5 megapascal, V1 is 0.2 meter cube, V2 is 0.05 meter cube, P1 and P1 V1 to the power n is equal to P2 V2 to the power n. So P2 would be P1 times V1 by V2 to the power n, or if you substitute the numerical values here, you will get P2 is equal to 3.0305 megapascal. Now we have that P1 V1 to the power n is equal to P to the power n. Okay, so volume V is P1 V1 to the power n by P, or to the power 1 by n. Okay, now change in entropy is enthalpy. So we have got the final pressure here. So change in enthalpy is integration of VdP from P1 to P2, and we got that V is P1 V1 to the power n by P to the power 1 by n. So P1 V1 to the power n is a constant, so that can be taken out of the integration. P1 V1 to the power n to the power 1 by n is taken out of the integration, and we integrate 1 by P to the power 1 by n. So you will get this. If you integrate it, you will get the limits from P1 to P2. You will get 1 minus 1 by n, P2 to the power 1 minus 1 by n, minus P1 to the power 1 minus 1 by n, divided by 1 minus 1 by n. If you simplify it, then you will get n times P2 V2 minus P1 V1 divided by n minus 1. And if you substitute numerical values here, because we know P2 as well, from this, you will get the change in enthalpy as 223.3 kilojoules. Okay, now we got that, we know that H is U plus PV. So H2 minus H1 is U2 plus P2 V2 minus U1 plus P1 V1, or U2 minus U1 is P2, or H2 minus H1 is U2 minus U1 plus P2 V2 minus P1 V1. We had to find the change in internal energy as well. So U2 minus U1 would be H2 minus H1 minus P2 V2 minus P1 V1. If you substitute the values of the enthalpy change and P2 V2 and P1 V1, you will get U1 minus U2 as 171.77 kilojoules. Okay, since this is a reversible adiabatic process, it's an isentropic process, so S2 minus S1 is equal to 0, because of this Q12 to be equal to 0. So the net work done from the first law we can find from the first law of thermodynamics, that is Q12 is U2 minus U1 plus W12, or W12 is U1 minus U2, because Q12 is equal to 0, or W12 is the negative of the change in the internal energy, that is minus 171.77 kilojoules. Okay, so I hope it is clear till now. So I think there is one more question. Yeah, so let us look into it once, and then I think we can stop for today. Okay, so yeah, this is the question. Let us look into it. Air is flowing, air is the working fluid here, is flowing steadily in an insulated duct. The pressure and the temperature measurements of air at the two stations A and B are given below. Establish the direction of the air flow in the duct. Assume that for air, Cp is constant, this is 1.005 kilojoule per kg Kelvin. H is Cpt, this enthalpy is Cp times temperature. V by T is 0.287 by P, where P, V and T are in kilopascal, meter cube per kg and Kelvin respectively. So the properties at station A are given here, properties at station B are given here. Okay, so what you can do is, right now you can pause the video for now. Let us try to see whether we are able to look into this thing, and then we can try to understand. So in this question they are asking us to find the direction of the airflow. Okay, so one way to look into is to find the change in the entropy of the universe. Okay, so if we assume that the flow is from A to B, okay, that is B is the final, the flow is from A to B would imply that station B is your final state and station A is your initial state. Okay, so with that argument, if you calculate the change in the entropy of the universe and find that it is coming negative, then it will imply that the chosen direction of your flow is wrong. So in that case, the flow should be from B to A, or otherwise, if you take the flow from A to B and find that the change in the entropy of the universe is positive, then your chosen direction of flow is correct. Okay, so that's one way to look into it. So you may pause the video now and let us try to look into the solution. Okay, so this is the value of the properties at the stations. Okay, so on thermodynamic property relations, we have TdS is equal to dH minus VdP, because this is something that is given in the question, the enthalpy relations and everything, so we can use this relation. Okay, if the internal energy relations are given, we could have used that internal energy as well, but since that is TdS equal to du plus PdV, but since the enthalpy relations are given, then we have to use that. Okay, so our TdS equal to dH minus VdP in terms of thermodynamic properties. Or ds is equal to dH by T minus V by T dP. Okay, so the change in the the entropy from A to B, considering the flow is from station A to station B, so station B with the final point and station A with the initial state, final state and initial state. So we will have the change in the enthalpy from A to B would be integration of Cp dt by T integrated from Ta to Tb minus 0.287. This V by T was 0.287. If I go here, so you can see V by T was 0.287 by P. That's why we use that relation here. So 0.287 by P negated from PA to PB. So if you do that, you will get SP minus SA is a 1.005 natural log of TB by TA minus 0.287 natural log of PB by PA. If you do that and take the temperatures at absolute temperature scale, you will get the change in entropy of the system to be minus 0.047 kilojoule per kg Kelvin. Now, since the duct is insulated, the change in entropy of the surrounding is zero, because the surrounding is not interacting with the system, so there is no change in the entropy of the surrounding because of its interaction with this particular system. Okay, so that's why if you consider this to be the direction of the flow, the change in entropy of the universe comes out to be 0.047 kilojoule per kg Kelvin. It's because delta S universe is delta S system plus delta S surrounding. Since and this is minus 0.047 plus delta surrounding is 0, so we will have delta S universe as minus 0.047 kilojoule per kg Kelvin. And since this is not possible, that's why the flow is from B to A. It is the assumed direction of the flow is wrong, and the flow must be in the opposite direction for the second law of thermodynamics to be satisfied. Okay, so I think that's all for today from my end, and thank you for bearing with me. I had to postpone these sessions, and it might have been quite difficult for the students as well as the course handlers. So I apologize from the depth of my heart for this inconvenience. But again, I could not miss this international conference as well. It was very important for my PhD, my work as well. So I couldn't miss that. But I tried my best to provide all the video recordings and conduct the sessions and the stipulated time. So thank you for being so understanding, and thank you for understanding my scenario. Okay, I'm sorry, and for the rest of the 3 scheduled classes and the extra class for the doubt clearing session would be conducted in the stipulated week. Okay, that's for sure. And thank you once again, and let's all meet next week, the week 10 discussions. Okay, thank you.